Hi everyone! In this video, we're going to talk about rules for simplifying algebraic expressions and how we can avoid common algebra mistakes when doing so. So first off, why do we want to simplify expressions? What's the point? So here we are given two different algebraic expressions. And if I told you that these expressions were equivalent, and I then asked you to find the value of them at x equals 4, which expression would you use to find that value? Well, personally, I would choose the one on the right because we only have two operations going on, 22 times x and then minus 2. So I could plug that 4 in for x right away. But if I look at the one on the left and I plug in 4 for x, I've got a lot to look at. I need to do what's in parentheses, and then I've got some extra multiplication in addition to do. So there's a lot more room for mistakes when we follow our order of operations for that expression on the left, whereas the one on the right, since they're equivalent, should get me the same answer and it takes me less calculations. And this expression on the right, 22x minus 2, that's the simplified algebraic expression of the one that's on the left. So what does it mean to simplify? How do we do this? So in a previous video and worksheet, we looked at how we could evaluate algebraic expressions when we're given certain values of x. But in this course, we're not always going to be given specific values. And if we have a lot of x's, sometimes that can be very overwhelming to look at, a long expression. And so we want to simplify them to help us make sense of what that expression could represent in a certain context. And so when we simplify them, we're trying to write them in the simplest way possible. And to do so, we're going to need to use some basic algebra rules. So some of these are things that you may have worked with in high school. If not, that's okay. We're going to go through some of them in the video. And these include order of operations, combining like terms, exponent and radical rules, and distribution properties of polynomials. So to explore these different strategies, we're going to look at some common mistakes, what went wrong, and then how we can fix it. So the first thing that we're going to look at is when we distribute a negative term to a polynomial. So here we have the expression -5 times the quantity x plus 7. And we can see that what this person chose to do in the next step was they did -5 times x, but then when they distributed to the second term, they just did 5 times 7 instead of -5 times 7. They dropped the negative sign. And so when we are distributing a negative, we need to make sure that that sign and number is being distributed to all terms in our parentheses. So let's go ahead and correct this mistake. Here's where they went wrong, and let's fix it. So if we have -5 times x plus 7, we're going to do what they did to start. They're going to do a -5 times x. But then we're also going to do a -5 times 7. So then we can do this multiplication. -5 times x is -5x. -5 times 7 is a -35. And so there is our simplified expression. So here, just remember that you're distributing the negative and that term, so the sign with the number, to all terms in the parentheses, not just the first one. The second mistake we're going to look at is when we raise a polynomial to a power. So here we have the expression x plus 2, and it's being raised to the second power. And what this person decided to do was they distributed the power. So they said, oh, we're going to do x squared and we're going to do 2 squared. And then they simplified 2 squared as 4. But they actually were wrong right away. Here's where they made their first mistake. So think about this in terms of numbers. So if I asked you to do 3 squared, well, the exponent would tell me how many times you're going to be multiplying 3 by itself. So in this case, we're multiplying 3 by itself 2 times. Well, it's the same thing with an expression. We're multiplying what's in parentheses by itself 2 times. So let's go ahead and expand this expression here. So I'm going to write this as x plus 2 times x plus 2. And so now we're going to make sure that we distribute every term in this first set of parentheses to every term in the second set of parentheses. And I'm going to draw some arrows to help us kind of organize this multiplication. So we're first going to do x times x, then we're going to do x times 2, then we'll have 2 times x and 2 times 2. So let's go ahead and write that out with our numbers and letters. So x times x, and then x times 2, plus 2 times x, and a positive 2 times 2. So now we can actually do the multiplication. X times x is x squared. X times 2 is a positive 2x. 2 times x is a positive 2x. And 2 times 2 is 4. We aren't quite done because we have some like terms here. We have 2x and 2x. We know that they're like terms because they have the same variable x, and it's being raised to the same power of 1. So we can add the coefficients, and what we'll get, we'll have x squared still. But a 2x plus a 2x, we get 4x, and then our plus 4. So here is our final answer. So remember, when we are raising a polynomial to a power, we need to expand that expression. We need to write it as how many times are we multiplying it by itself, just like we did here in our first step, and just like we do with our numbers. The next common mistake we're going to look at is when we can distribute a square root. So here we have the expression the square root of 9 plus 16. And what this person did was they said, okay, we're going to break up this addition with our square root. So we're going to do square root of 9, square root of 16, and then we're going to add. And so when they do this, they end up getting 7 as the value. But what if we did the addition first? Like if we treated this radical as parentheses and we followed our order of operations. So let's do what's under it first. Well, 9 plus 16, we get 25. And the square root of 25 is 5. But when we split up or distributed that square root, we got 7. And these are not equal. So that is one example of why we cannot distribute our radical over addition. And it's actually true for subtraction as well. We can't distribute that radical. But we can for multiplication and division. So let's see what happens if instead of adding, we were multiplying under the square root. So if we broke this up, we get the square root of 9 times the square root of 16. The square root of 9 is 3. The square root of 16 is 4. Multiplying those, we get 12. Well, what if we did the multiplication first and then did the square root? So let's see what we'll get. Well, 9 times 16 is 144. If we take the square root of 144, which is a perfect square, we get 12, which is exactly what we got when we broke it up. So that one does work. And again, like I said, you can also do this with division, but you cannot distribute over addition and subtraction, only multiplication and division. All right, Now, our last common mistake we're going to look at is multiplying polynomials. We've already done a little bit of this in our distributing a negative example and our polynomial raised to a power example. But in this case, we actually have a binomial, so a 2-term polynomial, times a trinomial, 3-term polynomial. And so what this person had decided to do is they said, okay, the 2x comes first in the first set of parentheses, the x squared comes first in the second set of parentheses, we're going to multiply those. And then we're going to multiply the second terms together, so the 1 times the 4x. And then, well, the negative 3 doesn't have a corresponding term, so it's just left alone. But this is not the case. We can't do this here. We're going to have to actually make sure that each term in the first set of parentheses is multiplied with each term in the second set of parentheses. So similar to what we did above, let's go ahead and draw those arrows to show that multiplication that has to be done. So I'm rewriting my expression. And then when we multiply, this 2x has to be multiplied with x squared. We're going to multiply it with 4x, and we're going to multiply it with negative 3. So we're distributing it to each term in the second parentheses. Same thing with the 1 times x squared, or 1 times 4x, and 1 times negative 3. So let's go ahead and write that out. So 2x times x squared. And then we have 2x times 4x. And then 2x times negative 3. And then distributing the 1, we get a positive 1 times x squared, positive 1 times 4x, and positive 1 times negative 3. So doing that multiplication, 2x times x squared, that gets us a 2x cubed. Remember, we add the exponents with our exponent rules. 2x times 4x, that multiplies to be 8x squared. 2x times negative 3, we get a negative 6x. And then positive 1 times x squared, we get a positive x squared. Positive 1 times 4x, we get a positive 4x. And positive 1 times negative 3 is a negative 3. We aren't quite done. We have to combine our like terms. So I see that we have an 8x squared and a 1x squared. And we have a negative 6x and a positive 4x. So we can combine each of those. Our 2x cubed is left alone. But then our 8x squared plus our 1x squared, we get a positive 9x squared. Negative 6x plus 4x, we get a negative 2x. And then we still have that minus 3. And so there is our final answer. So remember that when we're simplifying our algebraic expressions, if we're multiplying polynomials, we need to make sure that we distribute each term of one polynomial and multiply it by each term of the other polynomial. And don't forget to distribute those signs also, just like we saw in that first example. If we have a polynomial raised to a power, that means that we're multiplying the polynomial by itself that many times. And then it's just like multiplying polynomials. And then if we have radicals and roots of polynomials, those can only be distributed across multiplication and division. I hope you find this video helpful, and I wish you luck as you're simplifying your algebraic expressions.